All right, welcome to lesson 4 of unit 4. You are almost done. You're over the halfway point. So lesson 4 looks at combinations, which is a new form of kind of picking and arranging things. So up to this point, we've talked about permutations. So combinations, and we see this a little bit lower on the page, is when the order doesn't matter. The arrangement doesn't matter. It's a combination. When the arrangement is important, then it is a permutation. So far, order has mattered in everything we've looked at. But when we look at this first example, there's 3 people chosen for a committee from a group of 5 people. So we have 5 options. We've got person A, B, C, D, and E. We can only choose 3 of them, but it doesn't matter about order. So A, B, and C being chosen is the same thing as B, A, and C, because they're all still on the committee, and so is C, B, and A. All of those different arrangements, as long as they include only those 3 people, are all the same. So it's a very different process than permutations, because permutations would care which place they were in. So it would be like first place, second place, third place. President, vice president, treasurer. When we start designating very specific kind of places within the committee, then we care about order. But without that designation, it's just a committee of 3 people, and it doesn't matter the order they're selected in. Okay, so A, B, C, A, B, D, A, B, E are all the combinations with A and B. We could go A, C, D, A, C, E, and then A, D, E. And those are all the combinations we could have for A. Now A is done. We could go B, C, D, B, C, E, or B, D, E, but nothing else, because any other combination would have to include A, and we've already exhausted A. Okay, then we could also start with C. Well, C, D, E, and that's the only other option, because anything else would be exhausting A. We've already exhausted A and B, so we can't do any more. So in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 ways that we can do this. That's significantly less than if we started caring about order, because these aren't even all the ways that we could arrange just these 3 people getting chosen. Okay, so generally we would expect a combination calculation to be less than a permutation combination, or a permutation calculation. So the formula for this is NCR equals n factorial divided by r factorial and n minus r factorial. So this piece right here is what's new. Okay, taking out those, not only taking out the repeaters, but also taking out the possibilities of different arrangements within a particular set. Okay, and again, this stipulation at the end is strictly there so that we don't end up with a 0 in the denominator. And also because, so it's twofold, we avoid the 0 in the denominator, we also can't choose more things than we have to choose from. We can't select. Okay. You'll also see this notation where it's just n and r in the brackets. Either way, we rate it as n choose r, but both of these notations are combinations. Okay, and this one, I find that people see this one way less frequently and it throws them for a loop. Okay, and I don't believe that's even listed on our formula sheet. If I go back, formula sheet, yeah, when I look in here, we don't see that notation. So you could also see it as n r equals that. Okay. So going back, we're going to do some examples. So example 2 is strictly plug and chug. So again, in general, I'm just going to write my formula up here to refer back to, so I don't have to keep flipping pages. Okay, so I'm going to plug in my 5, remember, is n and r, so 5 factorial over 3 factorial, 2 factorial. Again, this will probably be in a calculator section, in which case you can just bust out your calculator and do the math. Or if it's on the non-calculator section, then it would be 5 times 4 times 3 factorial. And 2 factorial is just 2. So those would go away. This would simplify to 2, and my final answer would be 10. And so again, this is exactly what we did in that first example. We had 5 people to choose from, and we were choosing 3 people per committee. Okay, so we already kind of proved that that's true. So if you want to pause the video, give the next few a try. Make sure that you are conscious of doing all of these. The only one to watch out for, as usual, is when we throw 0 in there. If we're not choosing anyone, there is only one option. Okay, so pause it now and do these examples. Okay, so you should have gotten 70 and 1 for these 2 parts of example 2. So when we're looking at them, this one, again, you could have written it out like this, or you could have just plugged it into your calculator. For this one, in dealing with choosing only one thing, we've got 7 options. If you're only choosing one at a time, oh, that's incorrect. The answer is 7, because you could just choose each one individually, and there's no kind of other alternatives. So I didn't use my calculator for that, so that's where that came from. And again, if we're not choosing anything, there's only one option, not choosing anything. So example 3, let me zoom out a bit so the whole example is showing. In the Keno lottery, 20 numbers from 1 to 80 are chosen. How many combinations of 20 numbers are possible? So a key thing here is that it doesn't matter the order of numbers drawn. Doesn't matter. So if we know that, we definitely are affirmed by the question itself that we are using combinations. So the numbers 1 to 80 inclusive, so that would be 80 numbers to choose from. But we are only choosing 20. So again, we would plug this into our calculator. 80. And again, if you've watched that video, you saw that some calculators straight up let you plug this in. I'm always going to write down the formula strictly so that you can see it, so that if your calculator for some reason doesn't have that option, then we can use the formula. So it would be 20, 60. And then you would calculate it from there. So grab your calculator, make sure you know how to punch this in, either using the left-hand side, if you have that as an option, or the right-hand side using your factorials. Okay, so because these numbers are so incredibly large, I would imagine that this would be something that we would see on the calculator section. After typing it into my calculator, I'm reaffirmed that we are definitely going to see this kind of question on the calculator part of the exam, not the non-calculator part, because the answer is 3.535316142 times 10 to the 18, which is a whole lot of combinations. So you are totally fine to leave it in scientific notation. I feel like this is probably even truncated and there's more numbers back here that we just aren't able to see because my calculator display isn't long enough. And that's where graphing calculators come in. They will show you more decimal places unless you tell them to explicitly show you in scientific notation. But overall, the simple, basic scientific calculator will do your job, and that would be your answer. Okay. Example 4. How many different tickets are possible when playing the game Lotto 649? Okay, so the key thing to know is how on earth does Lotto 649 work? Lotto 649 works, you choose 6 numbers from, we're out of 1 to 49, no repeaters. And again, their order doesn't matter in terms of draw. And that's kind of uniform for every lottery. Okay, so just a couple notes there. So again, 1 to 49, so we have a choice of 49 different numbers. And we are choosing 6. So again, I'm going to use the button on my calculator that just lets me type this in, but in case you don't have that, I would put this into the formula as 49 divided by 6, 43 factorial. And then I would calculate it. I'd get 13,983,816 tickets. Okay, and specifically different tickets. So, as you can see from these examples, a big application of permutations and combinations comes into gambling and lotteries. It is not exclusively used for that, but it is a very common math when it comes to betting and casinos and that piece. Example 5. A local arena has 10 applicants interested in working in the snack bar. How many ways can 4 applicants be chosen? So 10 choosing 4. You have 210 ways to choose applicants or combinations. And 10 choose 6 also gives you 210 ways. So this alludes to something that we're going to start exploring in our next lesson. But there's some symmetry here. If you notice 4 versus 6 in comparison to 10, there's kind of a relationship there. Choosing 6 applicants versus choosing 4 to leave out would be another way of looking at it, in which case it's the same kind of process, same answer, so it kind of makes sense. Example 6. A new store must hire 3 cashiers and 4 stock clerks. There are 7 applicants for cashier and 8 applicants for store clerk. Okay, so let me just highlight. 3 cashiers is what we're hiring, but 7 applicants for cashiers. And then we've got 4 stock clerks that we're hiring, but 8 applicants. How many ways can the 7 employees be chosen? Okay, so the key thing here is that we need, out of 7 applicants, to choose 3, and we've got 8 applicants, choose 4. So we'd solve each of these separately. But then we would take them, and for every one way that we can do this, there are 70 ways we could have chosen our store clerks. So we need to multiply these together. Again, because for every one of these, there's 70 options that follow for my second decision. So I'm going to go 35 times 70. You could have also written from the beginning 7 choose 3 times 8 choose 4. That would also be totally fine, and then just plugging that into your calculator, whichever one makes more sense to you. Based on that, I have a total of 2,450 ways that I can choose employees. All of a sudden you understand why being a boss and hiring people becomes so hard. So example 7, an at least problem. So this is an interesting one because there's going to be multiple cases that we need to consider. Okay, so when we see the words at least, that should trigger something in your brain to say multiple cases. So there are 5 girls and 5 boys trying out for the water polo team. There need to be at least 3 girls at a time. How many combinations if there are 7 players total? So case 1 is our minimum. So of the 5 girls, and I'm always going to list girls first, just because that is my restriction. And I'll list boys second. Of the 5 girls, if I choose only 3, then if I've got 7 players total, I've got 4 people left to choose from. So I've got 5 boys. I'm going to choose 4 of them. But case 2 is if I choose 4 girls. Then for boys, I only have space for 3. And case 3 would be if I choose all 5 girls. Then I only actually have room for 2 boys on the team. So all of these are possible and fulfilled my requirements of at least 3 girls at a time. So I'd use my calculator to calculate each of these. And then I would add them all up. So 50, 50, 110 combinations is my final answer. So anytime you see some restrictions about at least, at most, you're going to have to go on a case-by-case basis. So just bear that one in mind. So I will be posting some homework to go along with this. There is going to be an assignment that looks at both permutations and combinations together. So definitely check on our Quest website for that. And we've only got 2 lessons left, and then you're done this unit. So keep up the good work.